Well, let's see if this works. I am going to talk about friction force in this video. Now, friction force is a force acting on an object, and it is a function of how well one object moves over a surface, or how two objects move over each other, sliding or not sliding. Now, the temptation is when you do your kinetic analysis is to accidentally identify two forces that end up being the same thing. So what do I mean? Well, when we talk about movements like running, walking, there is the ground reaction force acting on the person, specifically pushing on the foot, and the ground is pushing on the foot. The ground reaction force acts in three dimensions: vertical, anterior, posterior, and medial lateral. Okay, it's a three-dimensional force. Now, the temptation when doing a kinetic analysis, which what you do is identify all the forces acting on the object, not by the object. When you do a kinetic analysis, people will often want to identify the ground reaction force acting in three dimensions, and then add in another force called the friction force. What I want to do is convince you that the friction force is the ground reaction force, or one component of the ground reaction force. Specifically, it's the component of the ground reaction force that is parallel to the surface. So in locomotion on flat ground, we would call that the anterior posterior ground reaction force, and the medial lateral too, because you're preventing sliding on the side-to-side direction as well. So I'm going to try this and see if this makes sense. And then I will also add another video with some notes to explain what's going on here as well. So behind me is a computer monitor. It looks okay. And what I have on there is a graph of ground reaction force. So on the y-axis is force, okay? This is force. And this is the anterior posterior component of a force platform. I'm going to show you that in just a second. And on the x-axis is time, okay? So now let me orientate you a little bit more, bring the camera over, try not to get you dizzy here. All right. So right here, this is a force platform. It measures force in the vertical direction and in the anterior posterior direction, in this direction, both forward and backwards. And I've got parallel force, it says right here. You can't see that, but that's what it says. And it's pointing in these directions, meaning it's going to measure force in those two directions. Now, what I have on the computer right now is the ground reaction force in this parallel plane. So it's only showing one force, and that's the force horizontal parallel to this surface, okay? All right, so don't mind those data. I was just trying to make sure everything was working. I was trying to get the lines to show up as best as possible. Yeah, it's okay. So what I'm going to do, let me see if I can get both on the same time here. What I'm going to do is put an object on the force platform, and obviously it's not sliding, and I could push on it this way. And actually, I'll turn the force platform on in a second. And if I push on it this way, I should see a force pushing back against me, because what forces are acting on the object? Me pushing on the object, and the ground reaction force pushing this way. Because those two forces, which are the only forces in the horizontal direction, are adding up to zero. Acceleration is zero, meaning velocity is constant. Velocity right now is zero. So acceleration would be zero, velocity is going to remain zero. So as I push on this object, it's pushing back up. The ground is pushing back on the object and preventing the object from moving forward. Okay, two forces acting on the object, me pushing on the object, and the ground pushing on the object. They're going to add up to 0. Well, let me turn the force platform on. Let's see. Try to do that. So I'm hitting record. That's the tracing of the ground reaction force in the horizontal direction. If I push on it, oh, look at that. It's a negative force right in the middle. You can't see, but this is 0, okay? That's 0 force. And what happened? The force is negative. Why is it negative? Because I'm pushing on it that way. That's positive for the force platform. The ground is pushing in the opposite direction as me. That's friction, okay? That's the anterior-posterior ground reaction force. All right, I release it, it goes back up to 0. Again, nothing's moving. So the forces acting on the object have to add up to 0 in the horizontal plane. Horizontal plane, right now, there's no forces acting on the object in the horizontal plane. I push on it, that's a force. It's not moving, acceleration is 0, so all forces in the horizontal direction add up to 0. What other forces acting on it? The ground reaction force pushing on it in this direction to oppose me pushing on it. Now, I could push it and eventually, well, I'm sliding the whole thing. I could slide it, okay? Let me do that a different way, okay? Let me stop this. And I'll do it again. But now what I'm going to do, let's see. I'll get back a little bit. Okay, what I'm going to do is I'm going to tilt this up, okay? And I'm going to keep tilting, and I'm going to keep tilting, and I'm going to keep tilting it. And then what's going to happen, eventually it will slide off, hopefully. There's some traction tape on here. So why is the traction tape? To increase friction, to increase the ability of the surface to resist that object sliding off it. All right, so what am I going to be demonstrating here? What I'm demonstrating is a couple things. One is, as I lift this up, this is not moving. So the friction force is matching whatever force is pulling on the object in that direction. This force platform will measure force parallel to it. So as I pull it up here, it's actually measuring force in this direction, no longer horizontal. It's something at an angle to gravity. And I'll do this in the notes. We'll see this when we get to biking as well. As this goes upwards, the gravity force component stays vertical, but now what we're actually doing is increasing a pulling force due to gravity on the object as this gets steeper and steeper and steeper, okay? The parallel component of the force is going to be increasing as I tip it up, and eventually we're going to reach a force in the parallel to the surface that's going to exceed the maximum friction force that exists between these two objects. And once I exceed that force, the object will start sliding. My wife's downstairs. Hopefully she didn't hear that. All right. So let me turn the force platform on, and what we should see is a force that starts to increase, but at some point it's going to reach a maximum amount of force, and then the object's going to slide off the force platform. Okay, let's see. All right, so here we go. I'm lifting it up. The force is, I should have turned it around to make it a little easier, but it's negative, meaning it's pushing towards me, okay, to prevent that object from moving upwards. Hey, where's my data? Oh, it's still there. All right, now eventually, so now it's going to be a maximum, but a maximum negative force. I'm just going to slide, and it slides off, and the force goes back to 0. All right, so what do I have here? Let me stop that. This force, which is pushing, remember, the negative sign is just indicating that the force is acting in this direction, back towards me in the parallel to this surface. It's pushing in this direction. That's a negative force. So we would call that a maximum negative force. Maximum being the magnitude, and the negative sign just indicating direction of force application. Why is it pushing this way? Because as I tip this upwards, gravity is pulling downwards, and the parallel component of gravity is pushing or pulling that way. So the friction force is going to oppose that pulling force, and it's going to push in this direction, which is a negative force, which is exactly what we see. All right, so that maximum force is, looks like around 80 newtons. All right, we can actually figure that out based on this. Once that maximum force is reached, the object will then slide. That maximum force is a function of how this surface interacts with this surface, or specifically this surface, how it interacts with this surface. So what should happen if I can reduce that friction between these two surfaces? That force should be lower. Well, let me reduce the friction. I'll just put a smooth piece of wood here. And I'll put this back on. So intuitively, this is smoother. This is grippy tape on the surface here. This is now smoother. So what's going to happen? It's going to start sliding sooner when I start lifting it up. I won't get to that same angle that I got when I had the weight just on the force platform. And it's going to slide off sooner, meaning the friction force is less because the parallel component of gravity pulling down on the weight will be less as well. Again, I'll do that in the notes, and it might be easier to see the math of it. But let's just see what happens. Now, I got to be careful. This wood may slide off too, so I'm going to have to grab this in a way that I'm not pulling too hard on the wood and influencing the force here. But let's see what happens. All right, we're back to zero force. You can see that that's showing up. All right, now I'm going to start lifting it up. I'm not pulling on the wood so much, just trying to hold it in place. And we should see that weight slide off sooner. Ah, there we go. It did. In fact, that maximum negative force was only 50 newtons. What does that mean? That means the friction force between this surface and this surface was less. The maximum static friction force, okay? The maximum static friction force. Now, those of you who have seen graphs of forces and kinetic force, you'll notice this doesn't exactly look like that graph, and that's because this weight is falling off the force platform. If I had a longer flat force platform, I would see a little different graph, and again, I'll draw that out in the notes when I get to that part. All right, so smoother surface, less friction, easier to slide this object on that surface, and the force that we're measuring in the anterior posterior direction is the friction force. So when we do a kinetic analysis of this object, as I start lifting it up, what forces are acting on the object? Gravity and the ground reaction force, which is in 3 dimensions. And 1 dimension will be in the parallel direction here. And that's the force that the ground reaction force in that direction is the friction force. So you don't have to add 2 forces into your kinetic analysis. You do not add ground reaction force and friction force. Okay? If you add 3 dimensions of ground reaction force, you've covered it. Okay, friction force is just a special name forward force. That's all it is. And we can understand why people would slip, because now we can see that, and if I make this really even smoother and slippier and wax it down, and I do the same thing, it's going to slide off sooner, meaning that there's going to be less friction force. If there's less friction force, there's more ability for this object to slide off this. So it's easier to slip on a surface if you don't have a lot of friction or a lot of ability of the two surfaces to sort of stick together. Okay. All right, that's my demonstration of friction force. Hopefully it makes sense, and hopefully I'll do the notes next, and I'll have a video on that part, and by putting together this part of watching what's happening and looking at the notes, hopefully it makes some good sense. Okay, thanks.